try this
Okay,
one.
so our next speaker, as he's finishing setting up, is Pierre Weiss. And he's going to speak on generating sampling patterns in MRI. And he has a Halloween picture to start with.
Okay, so hello everybody. Thank you very much for inviting me. And well, this is the proof that Ubuntu is working even on a Mac. So I was not sure if my presentation would work. Okay, so I've decided to try to take the opportunity of being invited to present some results about the generation of sampling patterns in MRI. So that's a long-term project. We've been working on this for about 5 to 6 years. And I realized that some people in the room were interested, so I decided to do that. Okay, so this is not me, no. Okay, so the practical motivation behind that, my main goal today will be to reduce the scan times and improve the resolution in magnetic resonance imaging systems. And this may have plenty of advantages. You can reduce the costs. You can reduce the motion artifacts. By improving the resolution, you get a better understanding of pathologies and you improve the comfort. And money-wise, it's an important problem. For instance, I am working a lot with the CEA, and they are building a machine that is 300 million euros, so just a huge project. It's the biggest scanner in the world, and it's 11.7 Teslas, so just a huge machine. So my talk will be divided in 3 parts. In the first part, I will try to model the MRI system, so this is for a specialized audience somehow. The second part will be more generalistic, and then I will present practical results, in vivo results on a 7 Tesla scanner. Okay, so the first part is mostly, what I will present is mostly the results of discussions with those people. So the first woman there is Carole Lazaris, she's a PhD student. Then there was a previous PhD student, Nicolas Chauffer. Philippe Sussiou is the one who pushed for this project for like 5 years, and Alexandre Vigneault is an MR physicist. So the traditional way that mathematicians look at an MRI scanner is the following. You are given an image. In my talk, it will be U, pointer. Okay, U from omega to C, where omega is a subset of RD with D equal 2 or 3, depending on whether you are doing 2D scans or 3D scans. And an MRI system, the traditional way of seeing that is that it allows measuring pointwise sample of the Fourier transform. So you have an image, you compute its Fourier transform, and what you can do is measure pointwise Fourier values. For instance, you could do a random sampling pattern like this, where you are taking pointwise values. And on the theory of compressed sensing, at least, most people assume that the DXI belong to ZD, while actually the frequencies belong to RD. And the usual way what we try to do usually in compressed sensing is we try to minimize the number of measurements, because we assume that the scan time is proportional to this. So in fact, this model is not quite accurate. And my aim in this first part will be to make a more realistic model. But my description will still be very lacunary, so you can look, for instance, at this paper by Jeffrey Fessler to get somewhat more complete model. So the first important thing that will play a key role in my presentation is that you cannot really take point samples. The samples that you will take have to lie on a curve. So you take a curve, which is a function from 0t to RD, where t is the scanning time. And this curve has kinematic constraints. It has to have a bounded speed and a bounded acceleration. And what you can do actually is to measure your Fourier transform along this trajectory. So you are actually sampling the trajectory with a sampling period delta t here. So there are physical reasons for this, and so typically what you can do is a spiral like this. Okay. A second quite serious problem is that the signal is actually decaying over when you sample it. So you are actually not measuring a Fourier transform, but it's a bit complicated. It's like a Fourier transform of something that varies in time. But here I will not consider this effect. But this still means that you cannot sample all your space if you are doing high resolution with just one trajectory. You have to use multiple trajectories, like multiple spirals like this. And the sampling time will actually be proportional to the number of trajectories. That's more realistic than the number of measurements. Okay, so at this point, Anderson in the room may complain and tell me, okay, but the theories the mathematicians do are still okay because you can do pointwise sample in 2D and then use the third dimension to make continuous lines. And indeed, that's what the initial paper by Lustig, Dono, and Pauli were doing. The only limitation of that is that you have a limited range of target distributions. Basically, they are invariant in one direction. And the full versatility of the machine is not exploited. So I will try to go beyond that. Then here, this is an effect that is never taken into account. I found it in nowhere in the literature, and this is quite surprising because it's very important. You cannot actually measure pointwise sample, but what you can measure is integral of the Fourier transform along pieces of your trajectories with the sampling period. And since we found this nowhere in the literature, we decided to validate this with an MRI scanner, so we did that. We took a trajectory here, so it's just a zoom on the very central part of the Fourier domain. And here we took a large delta t, so we have few point samples. Those dots here are the Fourier measurements we get. And we try to reconstruct the image from these measurements. So this is what we obtain, and you see that you have serious contrast losses here. Then we do the same experiment, but we take 4 times as many measurements. So we divided here delta t by 4. And so we try to reconstruct the image from this, and you get this, and it's much better. So then you can complain, but here you have 4 times more measurements, so it's not you cannot compare. So what we do here is we take 1 sample out of 4 from these trajectories, and we reconstruct the image from this, and in fact we get the same. So here it's not because we had not enough samples here that we were not getting a good resolution. And finally, what we can do is we can take averages here of 4 consecutive samples and try to reconstruct the image from this, and we get nearly exactly the same result as this. So this is one way to validate this model here that appears nowhere in the literature. Okay, so that's an important fact. Another very serious effect is that your gradient coils, the things that allow you to travel in your Fourier domain, are imperfect. And also, when you put the body inside the magnetic field, it will change the magnetic fields. And so, in fact, you don't really know where you are sampling. You are sampling along your curve, but plus a perturbation here, epsilon of t, that is usually unknown. And this is really a critical effect. So typically, what you will get if you don't take this into account is an image like this that you cannot interpret. And while if you take it into account with, for instance, dedicated antennas, you can reconstruct this image. Then a third effect is that usually you have sensitivities, this is especially true in parallel MRI, meaning that you are not actually measuring the Fourier transform of u, but the Fourier transform of a sensitivity profile, so like this is like a diagonal matrix in infinite dimension, multiplied by u. And very often, this sensitivity here is unknown, and so you need to evaluate it from the data. And this is especially true when you have multiple antennas around your brain. Each of them will measure a different part of the signal. Okay.
Sorry, just to be clear there, S is a function of u.
No, not at all. It's a pointwise multiplication. So it's a function, like a smooth function that decays. For instance, here it would be high here and low here. It's just a pointwise multiplication. Yes. So then you have noise and blur. So you have additive noise. This is due, for instance, to your ADC. And you have quantization, and the quantization depends on your sampling time here, delta t. In addition, you have blur. So in all the previous equation, you are actually not measuring the true image U0, but a filter version of it. And so the images are intrinsically resolution limited in MRI. You cannot expect to have infinite resolution. So, okay, that was for the modeling, and so you see that you have plenty of things that happen in MRI. And I think that no theory, be it linear or nonlinear, accounts for all of this. So there are still plenty of open problems in sampling theory for those who are interested by that. Okay, so now I will go to the second part of my talk, which is how to generate sampling patterns. So I will, if you don't account for all the things that I've described, you will never get a good image on an MRI scanner. And I will not detail it too much, but we also generate the sampling patterns in a way to handle those effects. So this is mostly a joint work with people from Toulouse, while the previous one were a joint work with people from Paris. So there will be some optimal transport theory, and this is mostly with Jonas Kahn, Léo Lebray, and Frédéric de Gournay. And there will be another part with Claire Boyer, with her, and Nicolas Chauffard. So when you look at the literature about sampling theory, you have two competing theories, the Shannon sampling theory and the compressed tensing theory. And they are usually seen as something very different. So in particular, when you do linear reconstruction, which is basically the Shannon ID, you will learn that a good sampling set is a set of points, xi, which should have a controlled maximum distance, so meaning that each point in your space should have a point which is not too far from it, and this constant here should depend on the cutoff frequency of the function you want to recover. And also you should control the minimal distance between the samples, and here the idea is that you have samples that are too close to one another, then you will have redundant information that is not so useful to get good reconstruction. So to see this, you can, for instance, have a look at the paper. There is a review paper by Al-Roubi and Groschenig, which is quite interesting. And I also like this one because in this paper, this is an old paper where you learn that the optimal sampling set here is not the Euclidean grid, but rather the hexagonal grid. If you follow those two constraints, you will see that the hexagonal grid is better than this. So on the other hand, you have the compressive sampling theory, and here, so I will, this is the results here I show is a mix of the results, the early results by Candace, Ramberg, and Tao, and from people from here like Bernard Koch, Anderson Sen, Carrie Spoon, and Bogdan Roman. And here you take an orthogonal transform, for instance, which goes from sequence space to L2. And you assume that your image can be written as psi alpha, where alpha is S-sparse. And in MRI, you really need, and this is what is outlined here, to assume that the sparsity is structured. For instance, that the sparsity across the wavelet subbands is decreasing. And then under those assumptions, you can try to reconstruct your image by solving this convex program. So what you want is that when you take the Fourier transform of your reconstructed signal, and that you evaluate it at your sampling points, you want them to be consistent with the data you acquire. So there's a whole theory about that. And what is proved in ZenD, if you want to find a good sampling set, one way to do it is to generate a random sampling set. For instance, you can draw samples at random according to some density pi. Typically, in MRI, you would like to sample more the low frequencies than the high frequencies. Now, if you go to RD, the theory is really less developed, I think, and I think there are still many things to do in that realm. But from a practical experiment, what you can see is that the set X here can also be drawn at random according to some density pi, but also the samples should not be too close, and that's not something that appears in the standard theory. So, for instance, here we did a uniform random drawing. This is a point process, and you see that you have clusters, and typically this sampling set will be much worse than this one. So what you see here are the Voronoi cells, which basically should all have roughly the same volume for a sampling scheme to be good, and that you really observe that from a practical point of view. So when you say that, you begin to realize that Shannon and compressed tensing theories are not so different, because both theories tell you that a good sampling set should have a given density, so it should be uniform in the case of linear reconstruction, and non-uniform in the case of nonlinear reconstruction, and then they should respect minimal and maximal spacing between the samples. So to formalize, now we will try to use this observation to generate sampling patterns. So one way to formalize this is to see the sampling set as a discrete probability measure. So given a set of locations x, we can construct a probability measure, here mu of x, which is just a sum of the Dirac masses at the location xi. And it's normalized so that the mass is 1. And given a distance d, which goes from the set of probability measures to R, one way to generate a sampling scheme could be to try minimizing this distance, so mu of x with respect to the density pi, to the target density pi. And one question is how to choose this distance. So I will show you two things that you can do. And one of the things was motivated by this experiment. So here you have two images. This is an image of a lion, and this is like a dotted image. And you may wonder, so when you look at this image, you can recognize this one, and you may wonder why. And there is a simple way to explain this. It's I will make a blur of both images simultaneously. So here with sigma equal 1, sigma equal 2, sigma equal 3. And you see that at a given resolution, the images cannot be distinguished anymore. Okay. So that motivates the introduction of a distance, which is like this. So you take a blurring kernel, H, and you convolve both measures. And basically, this operation here, the convolution, allows to map a radon measure to L2. So, and then you can compare your two measures in L2. Okay, so that defines the distance. And when you have defined the distance over the space of measures, what you can do is try to optimize this distance with respect to the sampling set. So you can formalize it like this. So I let m of omega m denote the set of discrete measures with m point. So these measures. And if you want to find the dot's location, what you can do is try to minimize this distance with the constraint that your measure belongs to this space. So what you are trying to do is you are trying to project pi over this measure set. Okay, so that's a projection problem. And then you may wonder how to solve that from a numerical point of view. So it's not so easy, but the principle is quite easy, in fact. The idea is just to reparameterize this problem with respect to the location. So here, this space is highly non-convex. If you add two measures which have endpoints, you will get usually two endpoint measures. So, but if you look at this problem in the space of positions, you get this problem here, which is the sum of two energies. One is a repulsion potential, so an energy that will try to repulse the samples and the other one is an attraction potential, which will try to attract the xi toward the region of high masses of pi. And here the relationship between it's working now. Oh, incredible. The relationship between h and h here is a Fourier relationship like this. So in all my talk, I will choose this kernel here, an L2 distance, for some reason. And this may seem simple at first look, but if you look closely at the literature, you will realize that this is actually some instances of this problem actually encompass the Smale's 17th problem to solve for the 21st century. So that's actually an extremely complicated numerical problem. But you can still try to solve it with simple methods like a gradient descent with respect to the positions. And this is not my idea, this is actually an idea by mostly the German school. It started with Joachim Weickert and then other people worked on it like Gabi Steidl, Massimo Fornavier. And the idea is just to make a dynamical system, x dot, which goes according to this flow. So you compute the gradient of this distance with respect to your location. Okay, so here is an experiment. So we start from near arbitrary. So I just put all the points on a circle, and then you let the ODE flow, and this is what you obtain after some time. Okay, you get your mind. Okay. That's the principle. So I told you that we were also considering a different distance, and this was motivated by a discussion with Gabriel Perret, who's doing a lot of optimal transport. And here I will consider the semi-discrete optimal transport. So the idea is to take d, the distance d, as an optimal transportation distance. So, and I must say we spent like 1 year on this, and we had many very good ideas. And each time we had a new idea, we realized 1 week later that Quentin Mérigot had done it already. So if you really want to know more about this, I advise you to look at the literature by Quentin Mérigot, which is really comprehensive on the topic of semi-discrete optimal transport. There are many other people who are very good, but I especially recommend him. So this distance is well, if you never saw it, it will be difficult to follow, but I will try to make a very brief summary. The idea is that you define a set of transportation plan, which are mappings from RD to X, where X is your set of sampling points. And these transportation plans tell you each point of your domain where it should be mapped in your set of points. And you want that the mass that is transported at point xi is equal to 1 over m, because you want to map one measure to the other. So you have this extra constraint here. And then the transportation distance, this is the Wasserstein 2 transportation distance, is defined as the infimum over all transportation plans of this quantity, which basically tells you what is the price to transport a mass pi of x at point t of x. That's the interpretation. And then there is a kind of wonderful theorem there. I really find it wonderful. That tells you that this transportation plan in the semi-discrete setting cannot be arbitrary. It tells you that the reciprocal image of the xi are necessarily closed convex polygons, which are defined through something called Lagercell. So a Lagercell is a generalization of the Voronoi cell. So it's the set. So given a weight function here psi and a set of location x, the Lagercell is defined as the set of point xi such that this inequality is satisfied. So for instance, if you take psi to be 0, you want to find all the point xi which are all the point x which are closest to xi. So it's exactly the definition of the Voronoi cell. But here it's more general because you can inflate some parts of the space by changing those weights here. Okay. And when you make this nice remark, you can show that your Wasserstein distance is actually can actually be expressed as the maximum of a concave function over this vector psi. I skip the details. This is a bit technical, but it's okay. So when you want to minimize, what we want is to minimize this Wasserstein distance over the set of locations. So this is a min-max problem. And you can analyze this function. This is quite technical, and under some technical assumption, you can show that this function g here is concave with respect to psi, and C2 under really technical assumptions. And with respect to x, it's C1, but it's highly non-convex. And so you can compute. You can also compute explicitly the gradient of your transportation distance with respect to your localization. And if you do that, you realize that the optimality condition should be that the center of mass of your Lagercell coincides with the point xi. That's the optimality condition. And well, this leads to a natural numerical algorithms. All those remarks. That the idea is to first apply a Newton method to find the optimal weight here, psi star. Then this allows you to construct the Lagercell Li of x psi star. And then you can apply a first order method with respect to x, since you know the expression of the gradient. I will show you, so that's a picture. And here, so we took a set of points here. And what I told you is that each of these points will be transported to a convex polygon, which is a Lagercell like this. Okay, that's and then you can apply this algorithm. So here I show you some flow. So this is the first iteration. We start from a uniform grid. And we let the algorithm flow. Okay, and after a while we get a nice mosaic. Okay, so if you want to know comparisons between the box methods, they have their pros and cons, each of them. So the optimization is harder for optimal transport. There are plenty of dirty things that I hide under the carpet. It's better for convolutions because it's just a first order method. Then from a computational point of view, the convolution is based on computational harmonic analysis tools like the NUFT, while here it's more computational geometry, the power diagrams. The scaling to the dimension is much better for the convolutions because it's just linear, while here it's polynomial. So it's basically only working in dimension 2 and you have a large number of particles. The convolution is slower in 2D, so if you want to do 2D, I would advise this type of approach. And the quality of the result is good in each of the approaches. And there is a nice property that if you look at the minimizer of these, the global minimizer of these functionals, when you take a uniform pi, you get the hexagonal grid. So you get the best sampling pattern for the linear reconstruction theory. Okay. So, but our aim here was not to design pointwise sampling, but curve-wise sampling. And so here is how you can do it. You consider a space of admissible curves, lambda, so for instance the curves with bounded first and second order derivatives. And from this you can construct a space of measures which are defined as the push-forward measures of these curves with respect to the Lebesgue measure. So what does this mean? So you take a Borelian set B, and this push-forward measure here is defined of B is defined as the time spent by the curve in the set B. And when you've defined your set of measure spaces here, well, you can express the generation of sampling patterns exactly as I did previously as a projection problem, except that now you want to make a projection over this more complicated set, M of lambda. Okay. So this one is defined through an infinite dimensional parameterization, so you need to make a discretization. And you can show that you can always approximate a set defined like this by a set defined as discrete measures, except that here your sampling points should belong to some constrained set here, Sn. And the control here is in Hausdorff distance. It's a bit technical to control this precisely, but you can do it. And so for instance, in MRI, what you would like is to have curves with bounded first and second order derivatives. So you can define this set Sn here as the set of points that are the distance between consecutive points is less than alpha, and the second discrete order derivative is less than beta. And then you can apply basically the same first algorithms that I showed already, where you do, except that now you add a projection step here on this set of functions. So maybe let's just say that this projection step might be uneasy. So, but we have good algorithms to do that. So for instance, here I did something quite fun, I think. You have a cat here in red of length 1, and the objective was to project it onto the set of curves with length 2 and with bounded curvature. So this is highly non-convex, but an ADM type algorithm still converges. You can show that it still converges to a critical point, and so you see that you manage to inflate your cat. Yeah. So, and then yeah. Okay. I don't know what happened. Okay. No. Okay. I cannot see the pointer. Okay, so then you can try to project. So here we start from a random curve. So it's the woman, a famous painting by Vermeer, and we let it evolve a bit. We let it evolve according to the flow that I showed, and after a while you manage to get Mona Lisa. Okay. Marilyn Monroe, sorry. Then, well, you can play with this. There are plenty of things you can do. So, for instance, here we took a map of the crime in Philadelphia. You have small crimes like prostitution and so on. And so this is a density of the crime in Philadelphia. And then we use this to, so you have drones and with different types of kinematic constraints. And you want to make surveillance with your drones, and you can wonder what is the optimal way to do it. And so you can use this kind of algorithms to find kind of optimal trajectories. Okay. Then just you can take a video, just things that you can do, and then project it here. It's on the set of 30 segments with fixed length. So this is okay, nice picture. Or on the set of curves. You can make plenty of funny things. Okay. And our students, they are a big fan of Frédéric de Gournay, who's the collaborator, and so they managed to give a trajectory to this machine and to make a nice painting of their advisor, Frédéric de Gournay. Okay, so in fact, these are fun applications, but there are very serious and deep questions involved. The functionals that we are trying to minimize are really highly non-convex. And a very surprising effect is that whatever the initialization, you always get something good at the end. Okay, and right now we are trying to understand this phenomenon, but this is very extremely complex. So now I will go to the practical results. How much time do I have?
10 minutes.
10 minutes? Oh, this will be perfect.
15 minutes.
Okay, perfect. So and here that's joint work again with Carole Lazarus, Philippe Soucieux and Alexandre Vigneault. And so all the results I will present are in vivo results on a 7 Tesla scanner, a Siemens scanner, with T2 star contrast. So yes, there are plenty of complicated things with an MRI. And here we use T2 star contrast, which means that we are able to take long trajectories. So it's the ideal setting for the things that we are doing. So yeah, the principle of our algorithm is as follows. You take an initial guess, an initial trajectory, here just straight lines, and you take a target density, so here for instance the uniform measure, and then you feed that to the algorithm, and it will generate a more complicated trajectory which has a good density, the good target density. And physicists, the way they like looking at sampling schemes is they take the Fourier transform of it for some reason. And here you see that it's very structured, while here we have basically a Dirac mass. And physicists are very fond of these kinds of, they call it PSL. Okay, so here again, so then you let the algorithm flow. So I didn't say it, but it's multi-scale. So here you see how the trajectory is generated. Some time. Okay. And then you can use it to try reconstructing images. So in this first experiment, we are really just doing linear reconstruction with a uniform density. And so this is the reference image, which is obtained with the sequences given by the manufacturer. And so this is like the thing that we cannot do better than this, basically. And here this is a 256 by 256 image, and it takes 2 minutes and 20 seconds. So it's quite long time. And then we can use our trajectory and try to reconstruct the image. So here it just takes 16 seconds. And we get basically exactly the same quality, be it with a nonlinear reconstruction, L1 reconstruction, or a linear reconstruction based on gridding. So you can wonder, something very, very important here is that we are actually not doing undersampling, but we are doing oversampling. This is a critical point, and still we manage to reduce the scanning time. We take nearly like twice the number of measurements of this. And the reason is that what we did is we decreased the sampling period delta t as far as the machine allows. So this is something most physicists will never do, because by doing so you really decrease the signal-to-noise ratio you get per sample. But by doing this, you actually improve the resolution in your k-space, and it's much harder to get resolution than SNR. So it's really important that it's something that is not known, I think, in MRI, that you should take your sampling time as small as possible to gain in resolution in the Fourier domain. And so here we also compared with something the manufacturer provides, which is a grappa sequence for specialists. And it also takes 16 seconds, so, but here, yeah, the quality is definitely not the same. Okay. You cannot use this. So, okay, by basically doing oversampling, you can very strongly reduce the scanning times. And that's something quite surprising somehow. So then we tried also to do compressed sensing, and to do compressed sensing, you need to take a target density measure here, pi. And here there is a growing literature on how to choose this. Claire will speak about this afternoon also. And well, depending on the assumptions you do, you can do, for instance, sparsity by levels in the work of people from Cambridge. Gita-Kutinok are shearlet-based approach, where you have non-radial sampling patterns. You can also do learning to learn the density. And in this talk, I will simply choose manually optimized radial densities. In my opinion, it's good to take radial densities because you would like to have rotation invariance, ideally. And so, yeah, it's not clear that you want this, but If you have very anisotropic densities, well, it means that your reconstruction will not be the same if you rotate your sample inside the machine. That may be a problem sometimes. So here we start from a radial pattern. We feed it to our algorithm. So that's the algorithm, okay. And so on. Okay. And then we try to reconstruct the image. So here that's the reference. It's still 2 minutes 20. And here we are just doing a slight subsampling. Very slight sampling. We have 30% less samples than this. And this is the sparkling reconstruction, and this is the spiral reconstruction. And you see that basically the spiral is doing pretty well. So here we really optimize the spiral. So the spiral has been in the air for like 30 years, while this is completely new, so it's hard to compete. And the reason why the spiral is working so well is that you can approximate any radial density with a spiral. So it's not clear that our scheme can compete with it, but still they do. In fact, we have really less artifacts, and the reason why it's quite technical, it's related to the jittering error that I mentioned, the fact that you don't know exactly the localization of your samples. If you use our sampling trajectories, these errors will be basically random. Well, if you use a spiral, they will be very correlated, and so this is why you get plenty of artifacts. And this is with a radial trajectory that you should never use for yes, for doing anatomical MRI with high resolution. Never use radial. Okay. And then, okay, we try to push a bit. Sorry. We try to push a bit our algorithm with a high resolution image. So here it's 512 by 512. The sampling time is 4 minutes 42. And we get different acceleration factors like 10, 15, 20. And you see that the quality is nearly constant, whatever the acceleration factor. If you look closely, you will see that there is a slight blurring, but it's very, yeah, the quality would decrease much faster with the spiral sampling. And this is again related to this error in the trajectories. Okay. Yes, and the factor 20, I think nobody never did that before. So right now we are working hard on making the thing work in 3D. So this is our first 3D sampling trajectory. So it's very complicated. And here you cannot reproduce this with spirals. And we call them Mr. Messy trajectory. And that's basically the end of my talk. Okay, so thank you very much. Just some advertisement. Yeah.
Have you considered generating patterns with Frank-Wolf algorithm?
No. So you mean minimizing the same energies that we have with Frank-Wolf?
Yeah, because you generate like single points one after the other, and they come with provenance rates in terms of number of samples you need to approximate your density appropriately.
I don't know. I think no. Okay, we should discuss offline. I think, but yeah. I didn't consider it. Yeah.
Just regarding the comment you made on the fact that optimal transport and Hilbertian norms, they give similar results for sampling.
Yeah.
I'm wondering if it's because you don't consider two singular distributions. Because, for instance, if you have two distributions that are have density bounded by below, then these two things are equivalent. The optimal transport is like equivalent to a Sobolev norm. So maybe, I don't know if it's for very complicated distribution, maybe you would see a difference.
Yes, probably. I mean, here it's just a heuristic observation we made that for the kind of densities that we consider, they give visually, perceptually equivalent results, but that's we did not quantify this. So. Yeah, it's clear that you can construct examples where they would yield different results.
I think if you have maybe in high dimension or in if the density is a cluster along a complicated structure, maybe.
Yes, probably we are. Yeah.
Questions of what about robustness of these trajectories? Have you any investigations on how robust this is?
So what do you mean?
So either different types of images, different types of data, beginning with different influences of errors coming from acquisition, coming from transmission, and so on.
Yeah, so it's much more robust than the spiral to like the jittering errors, and that's technical. I can explain it offline. And then if you input different images and that you try to reconstruct your thing with these trajectories, it will most likely work quite well because they, for the classes of image that have the same sparsity pattern, basically. These types of things will work well for images that have a similar structure in the sense that they have a similar sparsity pattern. Yes.
Maybe a little technical question. So you have this C1 property
Of G? Yes.
Can you get more than C1? I mean, I'm not asking for C2, but some continuity.
So it's very technical there. It's really very technical. For instance, in psi, you are not Hölder. You are C2, but you are not Hölder. They are kinks. And so you could probably use semi-smooth Newton algorithms with respect to psi. With respect to x, you can. We did the analysis. It's very technical. You are C2 alpha under some technical assumption, but it's completely useless to try using a second order method with respect to the positions.
You have a Newton version which is not second order in the sense of C2, but you can have something which is LC1, Lipschitz continuous, but once differential.
Yes. So
which usually is faster than gradient, but I don't know whether.
no, again. So we tried. We made a full analysis of the regularity of these functions. With respect to mostly what we do is with respect to the dots location. With respect to psi, it's well known. With respect to the dots location, you can definitely do Newton. You are C2 alpha, but it's not working. It will work slow. It's highly non-convex. So already applying Newton and non-convex stuff is a bit dangerous. And then it's not working. I can give more insight later. Yeah.
How do you reconstruct from these trajectories? Like in the Cartesian case, I mean, usually you use like a uniform FT. What do you do in your case?
So when we do linear reconstruction, we just use regridding, the standard regridding algorithms by Fessler, for instance, or the Luft. Yeah.
Classical acquisition schemes used to improve to accelerate the acquisition process are known to introduce complicated spatial correlation schemes in the reconstructed data. Is it possible to avoid this using QM?
Yes, so I think this is related to this figure where you see that the spiral is generating many artifacts here. The reason is that, for instance, the epsilon of t here, the perturbation that you have, one model that you can have is a linear time invariant. So model. So instead of observing your spiral, you observe a convoluted version of it. And so it means that all your samples will be shrinked towards the origin, and so the perturbation will be highly correlated. In our case, we have plenty of circumvolutions, and so the jittering errors will be basically arbitrary, and this is why we get better. We don't get these artifacts here. That's thanks to the many circumvolutions of the scheme.
I mean, the reference image looks like it has artifacts in it as well, in some sense, right? Compared to the.
Yeah, so perhaps it has some aliasing already, and maybe here, But this is the thing that the manufacturer provides. In some sense, what we do is better because we use regularization here. Yes.
How does this scale with dimensions? Suppose you want to solve it in like 5D or 10D.
So with the semi-discrete optimal transportation, it would not scale because the computing the power diagrams scales as I don't remember, but it depends on the dimension, and the complexity is the square of the number of particles in 3D, for instance. So it does not scale. Like here, we need to make it's extremely complicated to make those simulations. We need multi-core programming, many things, and like we want to reach like 1 million particles. And so when you square this is just intractable. But for the convolution distance, it's just linear in the dimension, so it would work.
Just a quick question about robustness, because you also mentioned it earlier. When you now have your trajectories and you will program your gradient coils, they will obviously not do exactly what you want them to do. So
yes.
The trajectory will be slightly different.
Yes.
Did you actually check how, when you slightly perturb your trajectories that you generate, how this affects the image quality?
Yes, basically stable for the reasons I have already mentioned. And now we have bought a new antenna, which is 300,000 euros. I don't have any money, but they bought that. And this is a machine that allows measuring the errors in the trajectory. So soon we will be able to say why it's working so well.
Yeah.
Any other questions? Okay, well, great. Thanks for all the questions.